this is Song Hee Ra and welcome to another HSC science video on organic chemistry. So, what is organic chemistry? We are all familiar with organic cucumbers, organic soil, organic milk. If we notice, they're all called organic. But this is usually what we think of when we think of organic, something's being organic. But in chemistry, organic takes on a different meaning. In fact, it means carbon-based chemicals that has a covalent bond and is non-metal. A completely different thing from what we are used to with organic foods and organic products. The basic of organic chemistry is that chain of carbons that can reach up to 1,000 of them long. But we are going to be focusing on the first 10 today. That includes 1 carbon chain being meth, 2 carbon chain eth, 3 prop, 4 but, 5 pent, 6 hex, 7 hept, 8 oct, 9 non, and finally 10 dec. These are just the basic roots of each type of carbon. So let's take a look at 3 of these carbon-chained molecules: methane, ethane, and propane. Looking at methane, we see that, again, it is 1 carbon, so it is a meth. And the hydrogens are added after we write the first carbon. And then in the second example, ethane. Eth implies that there are 2 carbon chains. Keep in mind that we always write the carbons first before adding in the hydrogens. So in this case, we put 2 carbons chained together and the hydrogens on the remaining bonding sites. Same thing goes for propane, except now we got 3 carbons because prop implies that there is a 3 carbon chain. And again, we add the hydrogens after, making propane. But really looking at methane, ethane, and propane, we haven't discussed what the ending of ane is. All of them have the ending of ane, but why is it in all 3 of them? Well, this is because they are all alkynes. The alkyne ending made up of hydrogens and single bonds between the carbons. And the single bonds means that they are saturated carbons. They are so special because they are saturated carbons. But what does saturation actually mean? It means to reach the maximum number of hydrogens the molecule can hold. So the ane just implies that it is made up of hydrogens and just single bonds between the carbons. But with saturation, there has got to be unsaturation too, right? It can't be just saturation, right? Well, yes, in fact, 2 different ways: alkene and alkyne. Alkene means that there is at least 1 double bond between carbons. Alkyne means that at least 1 triple bond between carbons. Pretty similar, right? Both of these are unsaturated because they do not reach the maximum number of hydrogens the molecule can hold. Looking at their first example, this is propene. Why is it propene? Well, we got 3 carbons, and an ene implies that there is at least one double bond, and we can see that within the first carbon. So it is propene, which is also an unsaturated molecule. Looking at the second one on the bottom, this is propene. Why? Because there's a triple bond on the first carbon, and there are three carbons, meaning there's a three carbon chain. Now let's take an example at some practice problems to utilize this information we know to actually name the molecule. This is a very big jump, but it can help build our understanding of these alkanes, and their names can directly show what type of molecule it will be. So this first example, we can see that there is a total of 9 carbons, but really we are going to be narrowing it down first onto the longest carbon chain. Whenever you try to name any molecule, always search for the longest carbon chain. That will be the base of the molecule. In this case, there is 7, starting from the bottom, going up onto the top. Then the single bond. Then we notice that there are only single bonds, meaning that's an alkane. So combining hept and alkane, we get heptane. But what is that 4-ethyl? That seems so odd to be a dash, right? Well, actually, it makes quite a bit sense. In organic chemistry, when we're naming a molecule or a structure, the 4 implies that the attachment is located on the 4th carbon. In this case, it's a 2 carbon attachment, meaning that it's an ethyl group. So 4-ethyl heptane. Another example, pretty similar but a little bit more complicated. The name is 3,3-dimethyl-5-ethyl-octane. Or without the dashes, 3,3-dimethyl-5-ethyl-octane. Quite long and seems kind of daunting, right? Well, let's break it down. First, we gotta keep in mind the longest carbon chain. We can see that it is 8. How 8? Well, going from the bottom to the middle row, back down into the bottom row. So confusing, right? Because the longest carbon chain doesn't imply that it has to be in a linear line. It is just a link between all of these carbons. Now, once again, this is also an alkyne. Because why? It only contains single bonds. So, oct plus alkyne means octane. We got the base of our molecule. Now, what is the repeated 3, 3 in a di? That's so odd, right? Well, we know that looking on the 3rd carbon, there is 2 attachments, one at the side and one at the top. So we know that there's 2 attachments on that carbon. So we add the prefix di. But the type of attachment is also quite important. In this case, it's just 1 carbon, meaning that it's an methyl. So we got 2 methyl attachments on carbon 3. Thus, meaning that we must add dimethyl. The 3,3 is to imply that both of these methyl attachments are on the same carbon. So 3,3-dimethyl 5-ethyl octane. Of that name, we've only covered 2-3 big parts. We are missing 5-ethyl. Well, going back to the longest carbon chain, going from left to right, we know that there's another attachment onto the 5th carbon. And we can see that it is a 2-carbon chain long, meaning that is an ethyl group. So 3,3-dimethyl 5-ethyl octane. Pretty simple, right? Well, now we're on to our last example. This one seems really confusing at first. Like, why are they all so uniform? But this actually makes it quite easier to name. Like the name says, it looks pretty simple, right? 3,4,4,5 tetraethylheptane. Kind of long again, but it's actually quite more simple than you may think. Again, the first step is to always break down the longest carbon. We can look at it from multiple ways, from just going straight up and down, or going from straight side to side. But we can see that only gives us 3 or 5 carbons. So we gotta think of it in a less linear form. We start from the bottom, up onto the top, and then back onto the right side. That gives us a 7-long carbon chain, meaning hept. And we know that it is all single bonds, implying that it is an alkane. So, hept plus alkane equals heptane. Now let's focus onto the attachments. Since we want the smallest number first, we're going to look at the closest one, which is 1, 2, 3. The 3rd carbon, there's an attachment, a methyl attachment, because 2 carbon chains. So there's one at the 3rd carbon, but there also seems to be more of ethyl. If you look at either sides of the 4th carbon, there is also another attachment. So that's another 4, 4. So it's 3, 4, 4. And then on the last one, there is a 5th. So 3, 4, 4, 5. Tetra. Tetra is because there are 4 of these methyl attachments. And ethylheptane. So 3, 4, 4, 5. Tetraethylheptane. Again, go back to these examples and review if you are having a hard time understanding it. It takes a bit to finally understand why we look at these carbon chains in the way we do and not in such a linear form. So that's all for today. So thank you for watching, and I'll see you next.